Scientifically, we're in the early stages of exploring a new frontier of science, and Caltech wants to be preeminent in that area, the area of quantum information science. We have to be driven by curiosity, but with a vision of what in the long term can really change the way science is done and change industry. And in the case of the Center for Quantum Precision Measurement, one of the things that's providing the impetus for this building is Caltech's vision of the future of gravitational wave detection. And LIGO is one of the great examples of how Caltech had a vision of the future of science and stuck with it for decades and eventually made great things happen. I mean, a couple of black holes can be merging a few billion years ago, and then today a gravitational wave washes over the Earth, and we can detect that? It's just absurd. But it's not the end of the story.
The LIGO technology and gravitational waves, they're kind of at the limit of what they can do using conventional techniques. For us to go from detecting like 100 black holes per year to the place where we're really homing in to find out what happened right after the Big Bang and what happens at the black hole event horizon, all of those things require this super sensitivity improvement. As it turns out, the same tools that people use to keep the quantum computer from having a lot of errors, that same technique is used to make a quantum measurement better. And that idea of squeezing the noise so that there's no noise related to the thing that you're interested in, but there is a lot of noise for something else that we don't care about, that is exactly the phenomenon of quantum entanglement.
Now, Rana might have in mind detecting black holes from the distant reaches of the universe, and that's certainly a very worthy and exciting goal, and we're going to learn a lot from it. But the technological development that he's spearheading is going to impact other things beyond just gravitational wave detection. As we develop these new strategies for building more accurate sensors, I think it's going to impact everything in science. Let's take Manuel Endres's lab, for example. He's interested in manipulating single atoms with unprecedented precision.
I basically started to ask myself, okay, can you do it in a some sort of a more clever way? So instead of letting these atoms self-organize, can I organize them for kind of a little bossy sometimes? I want to like boss these atoms around and do exactly what I want. So the trick to really see quantum phenomena is to try to isolate systems extremely well from their environment. But then I can press a button and say, let's go, and then they start to interact very strongly, and then they start to entangle. And then we can keep track of all degrees of freedom, so I can measure everything.
And if you can get all the atoms to work together, what you can do is about 1 trillion times better, like a trillion times better than what you would normally think based on 20th century understanding.
In recent years, we've been studying both as theorists and in the laboratory new kinds of materials which make use of quantum mechanics in unprecedented ways.
My name is Shay Chen. I am a condensed matter theorist, and what that means is that I study materials. But the kind of system I'm interested in is so-called quantum many-body system. So it's not just one particle being here and there. It's tens of thousands or 10 to the 23rd number of particles being here and there at the same time. And the most exciting discovery is, of course, that yes, that when quantum mechanical particles get together, and especially when they strongly interact with each other, then they can actually do something amazing.
Caltech has a few people who are really experts both in quantum information theory but also in what we call strongly interacting quantum systems or condensed matter theory. It's kind of special actually. Caltech is the most well-equipped place in the world, I believe, to do this kind of research.
Quantum science should be all together. Of course, we belong to physics, we belong to engineering, we belong to math or even chemistry, but we are all studying the same system.
That's the hope. I think it's co-location together with interaction spaces and high quality lab space in the same building and directly connected to it. We don't have that at Caltech.
And it's really important to us. All of our good ideas, I think, come from this kind of casual, informal interaction.
It's just amazing how people from different perspective can see things very differently and then totally inspire each other. It's predictable, actually, that a new building, a new interaction space would lead to new ideas and a breakthrough in quantum science.